another concept, okay? Clock. All right, so this is also, you can imagine, right? So this is extremely important for sequential logic, right? Because we need to define what is past, right? What is present. So that's where we have to introduce the notion of time. When we talk about clock, right? So what comes to mind? Now we have wall clock, right? You guys are seeing the clock on the wall a lot. So there, we may have a clock hand. If the hour hand, it's gonna circle, right? It's gonna go from 1 to 12, right? And then circle back, right? We may also have a minute hand, or right? For minute hand 1 to 60, right? So we circle back. But this is basically what we use, right? In our daily life, in a digital system. Can you guys imagine what kind of clock do we build? Everything binary, right? What is simply kind of a clock do we build? Right? If you look at the wall clock, right? We basically oscillate, right? We circle from 1 to 12 or 1 to 60. For binary clock, what do we do? Yes, right? Very intuitive, right? What else can we do? So, right. Some of you are already thinking about how to implement this clock, right? So to navigate, right? Actually, this is simply kind of a oscillator, right? That we can build one navigate, right? So, but this actually, the clock circuitry is fairly complex, so because we want it to be stable. But at high level, right? We basically want to oscillate between 0 and 1. That's the clock, right? And this is how we represent the clock using this so-called waveform. All right, I am highlighting this thing in red because you guys will be dealing with waveform a lot in the labs and later on, right? In some of the problem sets, right? So make sure that you have an intuitive feel for waveform, right? Again, we are doing the oscillation here, right? It's here. So this indicates 0. This is 0, right? And then we go to 1, and then we come back down to 0, and then 1, and 0. This is sort of like, we have a wave, right? So waveform. So that's why it's called a waveform. And this is time, right? So basically this is from going from left to right, so we have time, right? Make sense? Right? This is 0, 1, 0, 1, 0, 1, 0, 1. Okay, so if this makes sense, let's talk about some of the important concepts. So we have something called triggering edge. So this is basically a transitional clock that captures input data. So what captures things? This is something that we're going to introduce. This is really related to flip-flops. Okay, but usually there are two kinds of a triggering edge. One is called a rising edge or positive edge. The other one is called a negative or falling edge. Okay, again, the name is fairly intuitive, right? It's basically, we go from 0 to 1, so that's or low to high, that's a rising edge, or we have right over here, so this is a falling edge. So from 1 to 0. Okay, actually, in most cases, okay, I cannot guarantee that in all cases we'll be focusing on rising edge, but in most cases in this lecture and also in class, so we'll be focusing on rising edge, right? Going from 0 to 1. And the moment that we have an edge, okay, the moment we have an edge, it's called a clock tick, right? Basically, the clock ticks the moment we have a triggering edge. All right, so this is the very basic concept of a digital binary clock, right? 0, 1, just oscillate. And let me introduce more terms. Some of those will be somewhat familiar to you guys. Right? Let's talk about clock period and clock frequency. Okay, so a clock period is also called cycle time. So we use these two terms interchangeably later on. So this is basically time, the absolute time. This is absolute time. Okay. So measure between the two successive transitions, basically two successive triggering edge. So let's say the triggering edge is rising edge. Okay. So we have two rising edge here, right? This is a rising edge. The next rising edge is over here, right? So between these two edges, we have the cycle time or clock period. Okay, right? Basically, this span is the clock period, right? Because this is a periodic signal, right? That's how we can. So that's why we define period. Right? This is a square-ish, right? This is not a sine wave. This is not a cosine wave. This is sort of square-ish wave, right? Since we are going to between 0 and 1. And later on, right, in many cases, right, so actually this waveform is a little more realistic since we have the ramp up and ramp down, right? But in many cases later on, we may just see a very square-ish curve like this. So this is the sort of more ideal waveform. We just immediately go from 0 to 1, and then immediately drops from 1 to 0. If you assume that this transition can happen fast enough. All right. Does that make sense? Right? Clock period, rising edge. Again, these are just a sort of abstract concept at the moment. But let me try to make it a little bit more concrete. Maybe this is slightly closer to you. These days, when you guys buy a CPU, right? Actually, one of you were asking about CPU early on, right? So what are the metrics do you pay attention to? So when you buy a new computer, so there's this important metric, clock frequency, right? So, or even for cell phone these days, right? It'll tell you first is the multi-core or how many cores you have, and then how fast does the core run. It will tell you is the 1 gigahertz or 2 gigahertz, right? Usually most of the devices these days, whether laptop or desktop or cell phone, so usually most of them, the frequencies are between 1 to 2 gigahertz. Right? So that's actually basically tells you how fast the internal clock runs in that CPU. Make sense, right? So later on, it'll be clear, right? Pretty soon. So in most cases, right, the higher the frequency, the better the performance, but not quite actually. Okay, it'll be more clear in the second half of this class, right? But this is an important metric, and the frequency is basically the inverse, right? So the reciprocal of the clock period. Right? Okay, so if we have a very slow clock, 1 millisecond, we have a frequency of 1 kilohertz, right? 2 nanoseconds, this is a 10 to the minus 9, right? You have 500 megahertz. So, and then we're talking about 500 picosecond. PS means picosecond. Pico means 10 to the minus 12, right? We are looking at, in this case, 2 gigahertz, right? So in most cases, right? So for your laptop or desktop, so this is roughly the clock period, 500 picosecond. So usually between 1 to 2 gigahertz. All right, so any more questions about clock? Okay, so if not, let's see how we can use it, right? So let's try to take one more look at this D-latch. So see here, so this is enable, right? See, we usually connect the clock. So usually there's a global clock signal on your chip. Of course, in many chips, right? So we do have multi-clock domains, but in this class, we assume that there's a global clock signal, okay? And the signal is gonna be used to synchronize things, right? That's something that we're gonna cover in a week or so, right? But usually we connect the clock to this enable signal. And we will see a behavior like this, right? So we have this, again, squarish waveform, right? So when the clock is high, the D-latch is open, right? Open means D-latch is accepting new input. Otherwise, it's closed, right? So the clock is oscillating, and the behavior of the D-latch is also oscillating, right? Between open, close, right? In this case, since we are connecting clock to the C signal, right? So if this is clear, then we can also draw a waveform for the D input. So this basically shows you how the D input changes. Okay, that's initially at 0, and then it goes up to 1, and then later comes back to 0. Right. So this is how the D input changes. Okay. Actually, the change of the D signal, right, does not have to synchronize with the change of the clock. Right. This is a separate signal. This is a separate input. Okay. So now let's look at how Q looks like, maybe I should just ask you. So, okay, let's look at Q. Okay, so in this period, let's look at this period. What is Q? Any guess? In this entire period, it's 1, right? Okay, because it was set to 1 when the latch is open, but now the latch is closed. It's holding state. Very good, right? So this is a corresponding waveform, right? So later on, you guys need to be really familiar with this waveform. Okay, this kind of waveform for debugging your design, debugging your own microprocessor and your own circuits, right? And Quartz is a giveaway, right, to debug this. You're going to be using another simulator. And over here, Q, right? So this is a signal, right? So basically, when it's open, right? See here. So when the latch is open, so initially D is 0, right? So Q is also 0, right? Q corresponds to D, right? Q directly corresponds to D, right? And when D rises, right? So there's a slight delay maybe, right? And Q also rises, right? And holds, right? Because D remains the same. Over here, right? So D changes from 1 to 0, but this is an important period, right? See here. This is a related question I asked you, right? So Q does not change right away because Q is closed, right? The D latch is closed. So Q changes over here, right? When the latch becomes open. All right. Okay, so this is D latch. And this is an important term. D latch is level sensitive. We're going to be seeing this term a lot. D latch level sensitive because that's really about the C, right? So when C is 1, so when C is at level 1 or level high, so D latch is open. When C is at level 0 or low level, D is closed. Okay, it's level sensitive. It's really about the level of C. So there's a 0 or 1. All right. Okay, if this is clear, let's move on to something a little bit more convoluted. Okay, and this is actually something very crucial for you guys to appreciate how the digital system works. This is something that we're going to be using a lot more than Latch. Okay, later on, when you build your own microprocessor, we'll only use something called Flipflop, okay, instead of Latch. It's actually an edge-sensitive device. Okay, so for today, I'll just introduce a basic concept. Next lecture, I'll give you guys even more exercises to help you appreciate what's going on with Flipflop. It's an interesting name, right? So by just looking at the name, you probably know, right? Can already guess. So we have two things, right? We have a pair of things. So it's actually composed of a pair of two D latches. It's a back-to-back. And just like D latch, we have a D input, and we have another input. This one will always usually connect to clock, right? And we have output. Right, so I'm going to talk about what exactly is edge sensitive. So D latch, unlike D latch, right? D latch captures things when the clock is high, right? But for D flip-flop or flip-flop, so we will just say D flip-flop. In most cases, the shorthand is just DFF or FF. Okay, so this is flip-flop. All right, so for DFF, it captures data at the triggering edge of the clock, not when the clock is low or not the clock when the clock is high. It captures things at the edge. It sounds sort of tricky, right? But it somehow managed to do that, right? It's an edge sensitive device. If it's not at the edge, regardless, right? So if not the edge, for now, let's just assume that edge, the triggering edge is a rising edge. Okay, it's a rising edge. It's not the edge. the D flip-flop is going to hold value. It's going to remember the past value. So this is the behavior of the D flip-flop. All right, so again, this is fairly abstract, right? Let's just look at the diagram. Don't be intimidated, right, by the inverters. So it's going to be very clear why are we inverting the clock in this case, right? But you can quickly, I guess, spot that we indeed have two latches, right? We have L1, first latch, second latch, L2. Okay. So let's try to reason about this. So when clock is low, is 0, is L1 open or closed? When clock is 0. We're looking at L1. When clock is 0, so see here, we are looking at this signal, right? Clock L1. So clock L1 is actually 1, right? So L1 is open, right? So then what is QL1? So this is basically I'm using this name, right, to name the output signal from the first latch. What is QL1? Very good. It's basically D, right? Then clock is low. So think of latch as a door, right? When it's open, it let things through. And D flop is actually a D flip-flop or DFX, like a two-door system. Okay, so this is intuition. So we first pass the first door, right? When clock is low. Does it make sense? Right? We are passing the first door. Okay, so but when clock is low, what's Q? Or Q next? What is Q? Yes, unfilled. It's basically the last Q, right? Because when clock, right, when clock is 0, so clock L2 is 0, right? We're going through two inverters here. And this latch, this is closed. Make sense? Right? So basically we only, so when clock is low, we only propagate, right, the D through the first door, through the first latch. Okay, so when exactly does this D value, new D, gets to the second, right, gets the final Q, gets to the second door? So that's where when clock goes from 0 to 1, when clock goes from 0 to 1, so is L1 still on? Latch 1? Latch 1 is closed, right? Latch 1 is closed. So QL1 is still D, right? Make sense? Right? Latch 1 is closed. So we are holding the previous value. And latch 2 now is open, right? And this Q becomes D. That's how we get to the second door. So when clock goes from 0 to 1, so this guy goes from, right? Clock L1 goes from 1 to 0. Clock L2 goes from 0 to 1. And that's how we can capture the input. So at the rising edge. Any questions? Okay, so this is a truth table. Again, this is actually one of the more counterintuitive concept, right? So how do we capture things at the edge? I'll try to give you guys more examples and exercise next time, but this is basically how it works, right? At the high level. So we have a two-door system. We have two latches. The first latch open when the clock is low. The second latch open when the clock is high, right? So right at that transition, so Q becomes the new D, right? So this is the truth table. Okay, so only when we have an edge, right? Okay, so we have, so Q will reflect D, right? Q net will reflect D. Otherwise, we are holding. Okay. All right, so this is the symbol. this is a symbol. See here. So this looks very similar to the latch, right? But pay attention to this triangle. So when we have a triangle here, it means that this signal is connecting to a clock. Okay. And this is actually D latch, but this is a D flip flop. So when you have a triangle, this is a D flip flop. Okay, this symbol. Right. Later on, we may not even tell you. So pay attention, right? Whether it's a latch or flip flop. All right. So one last slide. Okay. So I want to show you guys the waveform. Right. We already talked about this. Right. So when clock alternates, right, from 0 to 1, right, we're going to be seeing this, right, the latch open, close, right? But at any given time, only one latch will be open, right? At any given time. Right? Okay. So, and then we have D changes, right? So tell me, so this is D, right? Tell me what's the waveform for Q, right? When does Q change? So if we name this thing, right? So let's say this is the edge 1, edge 2, okay? When does Q becomes high? We can also, any ideas? E1, right? E1 at the first rising edge. Okay, so we can look at the intermediate output, right? So from L1, but this is an important thing. So this is Q. So see here, there's this transition, right? And this one coincide with this one, right? E1. So this is where the second latch opens, right? So later on, D also drops, right? See here, D drops, but Q, so see here, D drops, Q does not drop right away. Q drops at the second rising edge, at the next rising edge over here, E2. Yep, right, so this is really an edge sensitive device. Okay, so that's basically the flip-flop. And this is also the last slide for this lecture. I know some of you are asking about a negative edge, right? Really the falling edge, right? So we can talk about how we build a flip-flop that respond to the falling edge next time. All right, okay, so that's it for this lecture. I'll see you guys next week.